Hi, welcome back. So, we have discussed in the last video that there's cracking that occurs in the fuel pellets. And we've discussed that when there's a fuel pellet, it will crack in this direction rather than in this direction. So this direction is in the azimuthal direction. So the stress is in the azimuthal direction. What's azimuthal? Means that you have a circle here and the direction of the force is in this direction. The azimuthal direction is that, okay, if the force is in this direction, it's along the radius. I mean, the radius is the same, but there's a shift in the angle, like from here to here. Yep, the vector is pointing 90 degrees to the radius, so this is in the azimuthal direction. If you're talking about the axial direction, it means the direction of the force or direction of the stress that's happening is parallel to the axis. So this is parallel to the azimuth, because in the azimuthal direction the vectors are pointing in the circular direction. So this is parallel. These forces or stresses are parallel to the azimuthal vector. This one is parallel to the axial vector. Okay. Now, why does that happen? Well, for this we'll need to do some kind of a force balance. So let's say you have we can separate the fuel pellet, so-called, simply into something like this. You have a hot inside cylinder because of our temperature difference, pushing out on a cold outside cylinder. So let's just assume this hot cylinder inside is pressurizing the outside cold cylinder rather evenly. For example, it's pushing equally on all sides. Just a very simplified assumption. Okay. So let's do the azimuthal force balance. That means in this direction, in the circular direction, so-called, where the force is going this way. Force balance. So we will look at the top-down view of this so-called cylinder. Okay, they're supposed to be concentric circles, but these are two circles, alright? Okay, let me draw a bit nicer. Now, this is slightly better. Okay, so when we consider an object at rest, the forces should be able to cancel out. Okay, so inside there's pressure from the expanding interior pushing out across all these directions. Okay, and what happens is that there is some stress. This is the azimuthal stress that's pushing down, keeping this whole outside cylinder together. So if you just consider the upward versus downward forces, so this we consider that okay, let's just chop this cylinder in half. We consider only the top half. So on the top half of the cylinder, there's the pressure that's pushing it outwards radially. It's going outwards in this direction. All the pressure is going outwards, and then these two stresses along the azimuth are keeping this section of the cylinder nice and tight on this the other half. So what is the pressure, or what's the force by this azimuthal stress? Okay, so well, we can imagine the this fuel pellet will have a radius r, which is of course equals to d by 2, and then it will have some thickness delta. So this length here, it's very small thickness, is called delta. Okay, so on the inside, let's do this first. On the inside, okay, so yeah, we want to find that the force acting downwards in this, let's do a downward force. It's equals to this stress times the area. So what might this area be, you might ask? Well, it's pretty straightforward. It is this it is this area is this thickness times some length. Okay, what might be this length, you might ask? What is this length? Well, this is the length in the axial direction. Okay, because you see you want to calculate this area here. Yeah, you want to calculate this area, right? So you can imagine, okay. Alright, so this area here, so this is the thickness, this is the whole length of the cylinder. Okay, so yeah, calculating like this area-ish, I'm shading it here. So there's this thickness delta, this is the length L. So we'll just use some representative length dl to represent one small cut of this length. Okay, so area equals to delta dl, and the force downwards over here, the force downwards equals to sigma theta times the delta and dl. Okay, and it's not just sigma, it's yeah, it's sigma down the stress. So on one side you have delta and dl, so on the other side we also have to account for it. So that is 2 sigma delta dl. When dl is this so-called length here, one small part of this length here to represent the to so-called make up the area. Okay, so let's talk about the force exerted by this radial pressure that's coming from the inside. Okay, excuse me. So inside there will be some form of pressure. Okay, so this pressure, depending on the angle from the center, the force pointing upwards will be of differing magnitudes. When this theta equals to 0, okay, when this theta equals to 0, all of the pressure is so-called pointing upwards, or all the force is that is exerted by this pressure is pointing upwards. If this is 90 degrees, then there's no component of the force that is there because of the pressure that's pointing upwards. So there is like a cosine kind of function. Okay, well, sometimes we also use this angle here rather than this angle theta. So it's the angle from this flat line here to help us to represent the the force that's pointing upwards. So what we have, the force equals to the force dF. So we take the we have to integrate because this is kind of the force is kind of shifting gradually. So we need to sum up all the individual small forces, the vertical components of these small little forces that are acting on the outside of the cylinder. So the vertical component of the force is dA times P. So this small little area here times the P, pressure. So pressure is a scalar, so we'll just leave it there. The area vector will be pointing in this direction. So it will be this little small square. Then this vector will be pointing this way. So what is this area here? Yeah. What is that area? So firstly, we will need to have this direction. We have discussed before that in the axial direction we have a dl, which represents the area. So dA equals to dl. Okay, and then we will need a sine phi to represent the angular component of it. Then we need this length here as well. This length here, if let's say there's this square here, there is this length here. So it's dl, and then what is this? Well, for small angles, this will be r d theta on this side. Why? Because this is the radius r, and based on the length of a sector, we need to multiply the angle d theta inside, or actually in this case it's r d phi, since this is the angle we are talking about. So dl sine phi r d phi. Okay, so that is the area that's pointing in the vertical direction. So let's put r d phi sine phi. Okay. So now we need to integrate all of this. Well, let me close the door. It's a bit... Okay, never mind. Now the alarm is gone. Yeah, let's integrate this from theta equals to, or phi equals to 0 to phi equals to pi by 2. Okay, integrate df. Okay, PR, so there's a dl at the side. dl sine phi d phi. And this should be quite straightforward. PR dl cos phi, if I'm not wrong, negative cos phi from 0 to pi by 2. Okay. When you integrate the sign, it gets a negative cosine. Alright, so yep, PR TL let me check, see whether I make a mistake. Yeah. This should be a pi. Okay, anyway, we want to know why that is pi. So we are integrating not just from here to here, we have to integrate throughout the whole 180 degrees. So we are integrating across from 0 to pi, not 0 to pi by 2. Okay, now you just need to integrate this. Minus cos phi at 0 is minus 1. Okay. Alright, and it will be minus okay, so cos of 0 or minus cosine of 0, that will be minus 1, and minus cosine of pi. Okay, let me do this again. So this is the final minus initial. Yeah, this will be plus 1 minus minus 1. Okay, the math should be right. So there's a 2 PR dl. So F equals to PR dl, and this is by the pressure. So equating this to this, because there's a force balance, 2 sigma theta delta dl 2 sigma theta delta dl equals to 2 PR dl. So the dl kind of cancels out, and you have this sigma theta equals to 2 PR over 2 delta equals to PR over delta. And that's what we get for our azimuthal stress when it's at equilibrium. Okay, so let's compare this to the axial stress. So in the axial direction, there will be a force excuse me. Now there'll be a force pointing downwards and the force pointing upwards. Okay, so let's take a look at the bottom of the disc, or the bottom of the cylinder, so to speak. Yeah, let me draw it right on here. Okay, it's about the best I can draw. So there's a pressure actually pointing downwards, or rather pressure acting on the area pointing downwards, and at the side, this part, there will be some axial stress pointing upwards, sigma z. Okay, so what is the downward force? It's the pressure times area. It's P times pi r squared. So the force equals to this when it's pointing downwards. Now let us also find the upward force. So force downwards and then the force upwards is equals to, again, this sigma z times the area. So what is the area of this ring? Well, by right, if you want to consider it, it's pi r plus delta square minus pi r square. Okay? Okay, so this is the big area here. So So let's just expand that out. Pi r square 2 pi r delta plus delta squared minus pi r squared sigma z. Okay, these two will cancel. So you have 2 pi r delta plus delta squared sigma z. But because we are considering delta, the thickness of this to be very small, we can just ignore this part. We'll have sigma z 2 pi r delta. So when we want to equate the upward and downward forces, we'll just do it like so. Sigma z 2 pi r delta equals p times pi r squared. Now let's move everything down. The pi's will cancel and the r's will cancel. One r will cancel the square here. So sigma z equals to pr over 2 delta. Okay, so you can see that for the same pressure, twice the amount of azimuthal stress is required to hold the cylinder in place. So in effect, when cracking occurs, it will always be along the azimuthal direction. So my professor was saying this was like how a sausage splits in or breaks when you cook it. So he calls it the sausage equation, which is a very interesting way of remembering it. So kudos to him. So yeah, we are really concerned with cracking when there are temperature gradients. And does temperature gradients like this also affect the steels and metals making up the reactor pressure vessel? Absolutely. But because of the high thermal conductivity of the steels, it will happen, but to a lesser extent, because the inside does not get as hot. But cracking can still occur, especially during an emergency core cooling event. They call it the ECCS. ECCS, Emergency Core Cooling System. So let's say you have an earthquake event like that in Fukushima. What the reactor should really do, as it did in Fukushima, they should have a shutdown and emergency cooling. Why must the reactor still have emergency cooling after shutdown? Well, while the fusion has stopped, there is still radioactive decay, and that radioactive decay actually produces a fair amount of heat, which this emergency cooling helps to remove. So removes radioactive decay heat. And because there are lots of alphas, betas, and gammas still coming off the reactor, but hardly any more neutron radiation. So there's radioactive decay heat still, especially by those alphas. So you need the emergency core cooling system to cause this to happen. But what happens during the emergency core cooling system? When the ECCS is activated, there's lots of water getting pumped into the reactor pressure vessel using multiple diesel generators. And of course you want to have that many for safety reasons, so in case one failed, you still have a few more. But you know, the tsunami came and killed those generators, so we had a meltdown in Fukushima. But anyway, let's consider the reactor before the tsunami came. I'm generalizing to any kind of a light water reactor. So let's say you have this generic LWR. I'll just represent it by this cylinder. It's very overly simplified. Normally it's operating at around 300 degrees C, but now because you've pumped in a lot of cooling water, I'll just put this as CW for cooling water. Now that you have pumped lots of cooling water in, this can subject the reactor pressure vessel to sudden stresses because of the temperature. And now because neutrons embrittle the reactor pressure vessel, or PV, neutrons actually embrittle the reactor pressure vessel, as discussed before. This makes it more likely that cracks will go during the process. This is known as pressurized thermal shock. And of course, the reactor pressure vessel will crack in this direction. So when there are sudden changes, it doesn't just have to be a heating up event, it can be a very sudden cooling down event. What happens is that when the reactor pressure vessel, of course, is pressurized, when it's subject to a rapid cooling, it comes from rapid cooling. What happens is that because there's such a big temperature differential, there will be a shock that's happening. So imagine like yourself, you're taking a hot piece of glass from the oven and then you suddenly submerge it into ice water. The whole thing will start to crack. So this happens to the reactor pressure vessel as well. Of course, to a less dramatic extent, but it's still important to take note of. Now, there are some formulas actually describing this, and conceptually, they are not that complicated, but they involve a fair bit of engineering math, so I'll just skip this for now. The idea again is to use, for that process, is to use some of the solid mechanics to calculate some stress field during the cooling process, and if this stress field exceeds a certain threshold, the existing microcracks in the reactor pressure vessel will start to grow, and the reactor pressure vessel will either leak during this pressurized thermal shock or rupture. Hopefully we want a leak before a rupture. Okay, so this is also called PTS, pressurized thermal shock. And I've attached a few PDFs for your reference, but I'm skipping discussion of the crack and stress models in this case, but there are plenty of resources online. And what you should know, whether a crack self-propagates, you should know the Griffiths crack model, and the link to this video is in the description. So for this video, we have discussed the fuel pellets and why it has to crack in the azimuthal direction, and we have discussed why fuel pellets are susceptible to cracking in general in this direction, because there's a hot center and there's a big temperature differential between the hot insides and the cold outsides. And we have also discussed that for the light water reactor, this can happen as well, but it's due to emergency cooling. So if we have a reactor pressure vessel outside at about 300 degrees C, okay, and suddenly you are bringing 30 degrees C water, you're pumping it inside. The inside is cold, but the outside, the center bit of the reactor pressure vessel may be still a little bit hot. But if you pump this much water this quickly into the reactor core, if you pump this much water in, the insides of the reactor pressure vessel will cool a lot faster than the outsides, and then you'll have some kind of a pressurized thermal shock. So this is what I have for now. In the next video, we'll talk about the role neutrons have in this thermal process. So thanks very much. I'll see you next time. Bye-bye.